through.
Okay, no problem for me.
Okay, perfect. Thank you. So in material modeling, I would like to introduce the concept of integrated computational material engineering, which is basically the coupling of several disciplines. And I will explain that as we move forward. You will see that in additive manufacturing, we have a seamless interaction between the processing of the material and the final product performance. So we would like to find methods to calculate the process which affects the material structure, dictating the properties and the performance of the product. If we have these tools, then we have a means of finding the cause of a certain effect. Designers on the other side will be able to define their goals, what is the performance of the product, and how to achieve the goals. So the central part is how do we achieve the goal, avoiding defects, for example. The next slide, please. So the current engineering environment is shown on the left-hand side. It is very separated. So you have the computational engineering in a vertical of its own with simulation data management. On the other side, you have the material science and the material lifetime management. The computational team cannot work without material data, but they are still separated in different entities that they have to exchange information. Then we have a third entity that is design, and they manage the design in a product design management or the product PDM system. It's a separate discipline of its own. Large enterprises try to combine this information with the product lifetime management, the brown circle, and that will bring in the manufacturing and the corresponding cost. Then we have the overlays of information management and knowledge management. Now, this system works well as long as you can separate the material, the manufacturing process, and the final performance, as in the case of stamping, for example. But in the case of additive, you are actually creating your product and your material during the manufacturing process. So we need to have something which is closely integrated, as shown in this triangular diagram on the right-hand side. The next slide, please. So in a study performed in the United States, we would like to integrate all the different disciplines towards an integrated platform which gives us all information to make decisions correctly in early stages. The different disciplines will include models, multi-scale measurements, optimization schemes, decision-making tools. What is the uncertainty of a certain information? Statistical analysis. We need to verify and validate all this data. Informatics, we need a digital platform to do all of this work. We need to educate new engineers to use this vast amount of information and generally manage the computational infrastructure. In this study, the vision is to be achieved sometime in 2040. The next slide. Integradde has, as a project, has moved in a very strong way to fulfill that vision. You see on the left-hand side a schematic view of the additive manufacturing system where you have a designer accessing information about feedstock, about simulations, about the robot and the machine, and about the inspection tools available to him to make a decision on his design. All this information needs to be exchanged in a bidirectional manner. So data flow from one entity or one contributor to the other has to be ensured so that we can create a system which corrects itself once it identifies something is going wrong, and it should improve itself as we move forward in the future. So the first product may be a little bit critical, the second product will be much better, and so on. This will be done with the corresponding data gathering algorithms and artificial intelligence. The next slide, please. So in order to achieve all that, we developed a digital platform which is based on a digital thread. Basically, the lower layer is where we gather all data related to the process steps. In order for the different machines and contributors to communicate with that layer, we have a communication layer. This communication layer is based on Industry 4.0 standards. One of them is Automation ML. Since these entities are acting in different sites of a company or integrating information from different companies, OEMs, suppliers, and whatnot, we need to exchange that information across site boundaries. So we will need corresponding cybersecurity systems which dictate a large portion of this data structure. The system as it is supports 3 steps. The planning stage, where we have the design, the simulation, the decision to do something in a certain way. The second step is the actual manufacturing process, where we have sensors gathering information about the quality of the material and the product. And the third step is the characterization of what has been printed. So the technologies, the digital thread technologies applied are Automation ML, which is an Industry 4.0 standard. We use a RESTful API and blockchain to ensure the security of the exchange data. The pillars dictating how this is operating is data integrity. We have to make sure that the data is correctly gathered. It has to be interoperable, so we exchange it between the different entities and contributors to the system. It has to be traceable. This piece of information came from this machine or this step at that time with this material, and it has to be cyber secure. This system has been developed and deployed in different pilot lines, and the next slide shows an example of the modeling activities that can be performed. This is a complex diagram, flow diagram of information. I will start on the lower left-hand side, user requirements. So everything starts with what does the user need as a final product. Once we have the user requirement, the designers can be active. So topology optimization or standard design activities will be performed to create this new product or adapt an existing product. This design step needs to take manufacturing constraints into account. So additive manufacturing, as any other manufacturing route, does have its own requirements and limitations. We take these into account during the design stage. Once we have the design, we can then move to the actual planning of manufacturing, which is orientation. How are we going to position the part in the machine? And how is the robot or the laser to be moved to create that body? All of these steps require information coming from databases or coming from other simulations. So, for example, when you design something, you need to know information about the material. How strong is it? How does it behave in certain situations? But this information is related to heat-treated process parameters or heat-treated properties. Yeah, this is the material in its final stage. But during the process, during the actual manufacturing, this material is not completely finished yet. So we have to have properties which are as built. So there is a distinguishing between what stage are we in the process and what material properties need to be used. It's a fairly complex diagram with a lot of information, also coupling sensor data later on coming from the from the actual build or the actual printing process. I will explain more details in the next slides where we see more, let's say, images to explain more in detail. In the planning stage, you see on the upper right-hand side the digital platform, and the red box shows that we are in the planning stage for the process. In this particular simulation, we are looking at a very small section of the final product where we look at the heat, the laser source, the feedstock as it is provided to the melt pool, and we look at the melt pool dimensions. This is what we try to predict out of this model. How wide is the melt pool, how high, and how deep? The relevance of this information is when I know how wide the melt pool is, I know once this deposited line is finished, the laser needs to move to the right or the left by this distance. So I decide based on these dimensions how my robot motion is going to be. Based on the height of the melt pool, I know that my robot has to maintain a certain height or distance from my product. Otherwise, we will have collisions and the printing process will stop. Finally, the depth is very important because if the depth is not sufficient, you will have delamination. You will not be able to build a process. You will have only thin layers which do not connect together. So with this information, I can move to the next step on the next slide, where we look at how the material is going to provide. So when I have a melt pool, the melt pool cools down in a certain speed, so the cooling rate. The cooling rate is, from the metallurgical point of view, very important because it dictates material properties. Here we use the information from that very small scale model to perform thermodynamic calculations to assess feedstocks. So you buy powder from supplier 1, it costs €1. You buy another powder from the other supplier, it costs €2. So what's the difference? Is it just the price? Here in this case, we see that in one case we only get FCC, BCC, which are okay, they're okay, the phases are fine. But in the other case, the cheaper powder generates other phases. The last one is particularly concerning with a carbide, which will lead to the cracking of the material. So with this thermodynamic calculation, we are able to exclude certain feedstocks and guide the manufacturing engineers that buy powder A, it may be more expensive, but it will give you a higher quality. So the next step. So we go with the information about the melt pool. We design the motion of the robot and the laser, and we look at the design and create a build strategy. Here in this case, we take all that information and run a distortion analysis, and we see that the component will be built. There are no collisions. And we also see that the final shape of the component is very close to the original design, with a deviation of something like 0.5 millimeter maximum. For this kind of technology, it's acceptable. So now we say that the planning stage, everything is acceptable. We want to move forward. We move to the printing stage and we gather intelligence via sensors. Here we are looking at thermal emission of the melt pool, and what we see is that the lower layers of the component are cold, so low emission, and the higher layers, and especially in the diffuser region, we have very high emissions with very high temperatures. Does this fit well with our plan? Maybe. We can now, because we have interoperable data, during the printing process, we can compare with the previous simulation data online. So on the next slide, we will see a comparison of the online monitoring results with the simulation results. And we see a very good correlation where the simulations actually told us that the upper layers will be hot. Can you go one slide back? Sorry, I might be taking too much time.
This one?
So once the component is built, we can then scan it and confirm that it's conformal with the original pad, and the deviation is within the 0.5 millimeter we had discussed before. So the acceptance criteria are achieved, and we are able to say this product is good. There is much more detail with defects and whatnot, but because of time, I not include that. So in summary, on the next slide, excuse me, the ICME platform provides us a foundation for process modeling, material modeling, and provides for flexible databases to support design stages as well as manufacturing stage. We have a digital twin which gathers information from sensors and enables us to confirm the build process with virtual twins which were created during the planning stage. Using the database modeling, so digital twins and artificial intelligence, will enable us to improve the accuracy of predictions and the quality of products as this system is deployed for many future products as we go further. And it is also not only deployed for this one aerospace pilot line, but it has been deployed in multiple pilot lines where we look at automotive products as well as machinery. Thank you very much.
Thank you, Mustafa, for your presentation.